Hello, my name is Alejandra Mercado and I'm with the Masters in Telecommunications program at the University of Maryland at College Park. Today we're going to be talking about recurrent neural networks for engineers. RNNs are typically used in sequence-to-sequence mappings. For example, if you want to translate text from, say, English to French or something like that. The novelty of the RNN is that they use feedback in addition to the input features. And the way that we're going to interpret it today is from an engineering perspective, looking at an RNN as a nonlinear discrete time dynamic system with feedback. So this is almost like the kind of equation that you would see in linear systems. The only difference is that we have a nonlinear function there, which we're going to talk about soon. So the state here we're representing as the vector h, and at timestamp n, the input or the input feature, or as engineers would call it, the driving vector, we call it x. And the input weight matrix is the one that pre-multiplies the vector x. Then the internal state h has a feedback element here. In this case, there's a single tap feedback h at time n-1. And then the weight matrix that multiplies the previous state. In addition to that, we have a bias vector, as we always do with neural networks, and a nonlinear activation function. We're also going to talk about that later. And we also have the output weight matrix to make sure that the information that's coming out of the activation function is in the correct format. We're going to be talking about each and every one of these individually. Engineers often prefer to learn things from the format of a block diagram. So let's look at a block diagram of our equation here. And just to remind us of what we're doing at each step, I'm copying the equation at the bottom of this slide. And we're going to start like we did before at the output, the state, h of n, the vector h of n. And I always understand block diagrams better coming from the output of an adder. So we're going to head towards the first adder. So the output state heads into a single delay. So we get the state at the previous time step, h at time n-1. And then that gets pre-multiplied by the recurrent weight matrix w. And you can see in the equation below what the highlighted yellow part describes what we're doing in the block diagram, and that heads into the adder. So what else goes into the adder? Well, let's look. First is the input feature x, right? That would be the driving function. That goes into the input weight matrix. So the output would be the feature pre-multiplied by u, the weight matrix, and these two guys get added together. And we get the two first summands inside of the activation function. Now the next thing that happens, as you can see in the equation, is that we add the bias term. So we get the bias vector that gets added to what we have so far. And the output of that second adder is actually the entire argument of our activation function. So that gets fed into the nonlinear activation function, and that could be a ReLU, that could be sigmoid, that could be any typical activation function that you're used to working with, which is going to be, it's going to add the nonlinearity of any neural network. And finally, we need to get our vector, the output of the activation function, in the proper format for the state. So that's what the purpose of the v vector is going to be. Now, in today's lecture, we're not focusing on training. That's going to come later. We're just talking about what are the elements that we're seeing here and what is the contribution or the importance of each one. In other words, from an engineering perspective, why do we need each one of these elements? And that's what we're going to talk about right now with an example. We're going to look at an example, and in this case, it's going to be a toy example. It's not going to be a learned RNN. We're not trying to find out how to learn how to train RNNs yet, because that's going to be in our next lecture. What we're going to see here is how each individual element contributes. So let's look at an example that predicts how to finish a short sentence. And the options are either Alice sleeps, Alice sits, or Alice exercises. And here are the rules. Alice is going to rotate her health schedule every day. So let's say the first day she's going to do exercise. Then the following day, the second day, she's going to sleep it off. And then on the third day, she's going to spend the day sitting and relaxing. And then the day after that, she exercises, then sleeps, then sits, exercises, sleeps, sits. She's going to rotate through that. Now, this is the component of the RNN that requires feedback. I need to know what Alice did yesterday in order to know what she's going to do today, and each day it's going to be like that. However, and this is where the feature input comes in, if Alice wakes up feeling very tired, she's willing to break her schedule and sleep that day off. And then the next day she's going to pick up her regular routine. Another possible input feature is that if she wakes up feeling particularly rested and energetic. If Alice wakes up feeling rested and energetic, again, she's going to ignore her schedule, and that day she's going to take advantage of that energy and do exercise. And then the next day she's going to pick up her routine schedule. So these are the parts where Alice rotates her health schedule, requires feedback, and the other two where she sort of breaks her schedule, that's going to require the feature input. The best way to envision this is if we see a block diagram. Here's our RNN, and there's a delay block, which is really internal to the RNN, but I'm leaving it out here just for visual clarity. So into the RNN comes the input feature. How did Alice wake up? Did she feel tired? Did she feel rested? Did she feel normal? The output state is the current state, but we need the delay version of the output for feedback because we want to make sure that the feedback allows us to keep track of the regular sequence of what Alice does when she feels normal. So let's look at the initial condition. The initial condition, let's say that the activity that Alice has is Alice exercises. So that's at time 0. At time equal 1, let's say on Monday, Alice feels normal. Yesterday, on Sunday, Alice exercised. So we know that she'll follow, because she woke up not feeling normal, she's actually going to follow her routine, which means that today, she's going to sleep. Now let's change the time to stamp 2. Alice sleeps now becomes the feedback. She wakes up feeling tired. Now we know that under normal circumstances, the day after Alice sleeps in, she would spend the day sitting down. But because we have an input that says she feels tired, Alice sleeps, ignores her schedule, and sleeps again. So this, for time stamp equal to 3, turns this Alice sleeps into feedback. And today, Tuesday, she wakes up feeling normal. And when she feels normal, we know that she follows her routine. And what comes after Alice sleeps is Alice sits. So the output is Alice sits. For time stamp 4, day number 4, the Alice sits becomes the feedback, and the input is that Alice woke up feeling rested. If it were a normal day, the routine would say that the day after Alice sits, she would exercise. In this case, we're ignoring that rule, and we're going to look at the input that says that Alice feels rested. Now, it so happens that when she feels rested, she also exercises, which is perfectly fine. It just so happens that the two happen to coincide. Now, for day equal 5, the Alice exercises become the feedback from yesterday, and on day 5, Alice wakes up feeling normal, which means that she follows her regular routine. And her regular routine says that the day after exercising, if she wakes up feeling normal, she would sleep. So the output for n equals 5 is Alice sleeps. Now, all this should be represented by our dynamic equation. And we know that the feedback part, W, has to provide options for us that are either Alice is following her routine, in which case you have to keep track of what she did yesterday in order to know what she's going to do today. So that's feedback there. But it also has to provide options for what if the input is she's feeling tired, in which case she's going to be sleeping, or the input is she's feeling rested, in which case she's going to be exercising. The W has to provide options for all three of these. Now, the input or driving force feature, which we're going to see a little bit later, is the one that's selected to emphasize which one of the three you're going to be using. Either Alice is following the routine, or Alice is sleeping today because she woke up tired, or Alice is exercising today because she woke up rested and energetic. We're going to see that later. For now, let's focus on W. What W would allow us to keep these three options open for us and only allow the driving force or the feature input to select which one gets activated? Since we're going to be talking not about training, that's on the next class, we're just going to be talking about the contribution of each of these matrices. We're going to use one-hot vectors to keep the matrices very easy to determine. So let's look at the state vectors. The verbs that complete the sentence are either Alice exercises, which we represent as 1, 0, 0, or Alice sleeps, which we represent as 0, 1, 0, or Alice sits, which is 0, 0, 1. Now, the way that her normal routine works is if on Monday she exercises, then on Tuesday she'll sleep in, on Wednesday she'll spend the day sitting, on Thursday she's going to exercise again, on Friday she's going to sleep in again, and on Saturday she's going to spend the day sitting and then exercise, sleep, sitting, etc. And this will be cycling through. The feature input vectors or the driving forces are either normal, she woke up feeling normal, in which case she's going to follow her routine, and we represent that by 1, 0, 0. Or she woke up feeling tired, in which case she's going to sleep that day, sleep in, so it's 0, 1, 0. Or she woke up feeling rested and energetic, and she feels like exercising an extra day, in which case we represent that by 0, 0, 1. Now, you may want to make a screenshot of these vectors to keep track of what a routine is so that we can identify the reason for defining the different matrices. Now, let's remind ourselves of the equation for the system dynamics. In this case, we're going to choose W to have this form, and we're going to see why in 1 second. Now, the top third of W is chosen to keep track of what happens next on her regular routine. So this W is going to pre-multiply the feedback. If the feedback happens to be exercises, that's 1, 0, 0, that means then this feedback is going to grab the first column of W, and that would reflect 0, 1, 0. That means that today she sleeps. If the feedback were today she sleeps, that means it would grab the second column, and that would be 0, 0, 1, which is today she sits. And if the feedback is today she sits, or yesterday she sat, that means that it would grab the third column, and that would represent 1, 0, 0, which is today she exercises. If yesterday she was sitting, today she's exercising. So this top third of the matrix keeps track of what happens next on her regular routine. But we also need to keep in mind that her regular routine may be interrupted, which is why we look at this second portion of W. Now, this second portion of W provides options for sleeps if the input feature over here requires her to sleep because she woke up feeling tired. If she woke up feeling tired, then I don't care what the input is from her feedback. I want her to choose sleeps, 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 no matter what the feedback is. Similarly, if she woke up feeling very rested and energetic, then I don't care what the feedback is from yesterday. The output in this case should always be exercises for all three cases. So this W provides us for all three options, whether it's routine, so she follows the cycle, or whether she woke up rested, or whether she woke up tired. Let's test it to make sure that we've got this right. Let's see if this guy's doing his job correctly. Let's say that in the previous state, in other words, yesterday, Alice was exercising. That means that the state at timestamp n-1 was that she was exercising. So we post-multiply, according to our formula, we post-multiply W by Alice's exercising, which is yesterday's activities. Now we know that when you post-multiply a matrix by a column vector that just has a single 1 in it and everything else is 0, you're basically plucking a column of that matrix. And in this particular case, because the 1 is in the first direction, in the first position, we're grabbing the first column of W. So the answer of this matrix multiplication is the column 1 of W. We just can go ahead and copy this column 1 over here, and let's analyze what it does. The first 3 points are the next activity, the next verb in the routine, which is after exercising, it is sleeping, which is the 0, 1, 0, which is right there. But we also need options in case she woke up tired or woke up rested. So the next segment is going to be Alice sleeps, no matter what she did yesterday, because she may have woken up tired. And finally, she may have woken up really rested and energetic, in which case that we need an option for Alice exercises regardless of what she was doing yesterday. Let's check the next possibility. Let's say that the previous state, in other words, yesterday, Alice was sleeping. Now, this is the vector for sleeping, right? We post-multiply yesterday's activity to W. And again, this is a vector that has all zeros except for a single one in position number 2. That means that this is going to grab column 2 of the matrix W. So we go ahead and copy column 2 from here to here. And we see now that the next activity, the next verb in the routine is Alice sits. This is sits. And again, in case that she woke up tired, we need a segment that has Alice sleeps. And in case she woke up energetic, we have one for Alice exercises. Last test to see if we're on the right track. Let's say that yesterday Alice was sitting. In other words, H at timestamp n-1 is 0, 0, 1. So we go ahead and post-multiply W by H n-1. This vector here is going to grab column 3 of W, and that we just copied this column 3 over here. And again, we verify that it's doing what we want. This guy says that the next verb in the routine is Alice exercises, which is correct. But we still need the option of Alice sleeps in case she woke up tired, and finally we need the option for Alice exercises if the feature says that she woke up really rested and energetic. So this W does the job. For every single feedback possibility, all 3 feedback possibilities, it does the job correctly. The next part we're going to address is how do we find a proper matrix U to pre-multiply the input feature or the driving force. So that's our job that we're going to address next. Now, again, by inspection, I chose this matrix for U. And you might argue it's not the optimal matrix, and that's fine. I just wanted to make this lecture as clear as possible. So this is not going for optimality, and it's certainly not going for training. This is just by inspection a matrix that works. So let's look at each one of the segments. The top third of the matrix U is going to be adding 1 to whatever is next in the regular routine. If the input is normal, we're going to add 1 to the next activity and zeros everywhere else. The next third of the matrix U adds 1s to the sleep verb if the input happens to be tired, and zeros everywhere else. And finally, the last third of our matrix U adds 1s to the exercise verb if the input happens to be rested and energetic, and it adds zeros everywhere else. And I'd like to point out at this point that I'm sure you could argue, wouldn't it be smarter instead of adding zeros to replace the zeros with -1 or something? Because in addition to emphasizing the verb that we want by adding 1, we could de-emphasize the ones that we don't want by adding -2 or -1 or something like that to all the wrong options. That's true, you could do that, and I'm sure you could sit down and come up with a better U, but I wanted to show you the purpose of the bias vector. And by leaving all those added points as 0, it's a very clear indicator of the usefulness of the bias vector. So I'm just going to leave you the way it is right now. And we're going to test it. So we start again looking at our equation. And let's move it down to make a little bit of space. In order to test the new U, I need to have both the feedback and the driving function. So let's say that in the previous state, Alice was exercising. Yesterday, Alice was exercising, so this is the vector for exercising. And we're going to highlight here the contribution within the argument of the activation function for the feedback is W. This is the W we went over already. And in this case, Alice was exercising yesterday, so that is the vector that post-multiplies W. Next, we need the current driving force or feature input. And let's say that Alice woke up feeling normal today. And this is the vector for feeling normal. So we're now going to add this contribution in blue. We're going to use the U matrix that we already looked at, and the vector for woke up feeling normal is that. Now, we know that when you post-multiply a matrix like this with a single 1, everything else is 0 in the first position. That means we grab the first column. There's the first column right there. And in this case, same thing happens. We have a vector of all zeros except a 1 in the first position. That means I grab the first column. There's the first column right there. Now we do element by element addition, and we get this output. Now, what we would like is to follow the routine, because today Alice woke up feeling normal. When she wakes up feeling normal, she follows her routine. And her routine is that if yesterday she was exercising, then today she's going to sleep it off. So we would like the sleep option to be very big and emphasized, and everything else that has to do with irregular days, like when she wakes up tired or when she wakes up energetic, these guys should all be 0. Now, in order to make that happen, we're going to select the bias vector and the nonlinear activation function to make sure that that happens. Now, the bias vector that we're going to introduce here is going to be constant and just -1s all along, 9 -1s in a column vector. And the activation function that we're going to use in this occasion is the ReLU. So basically, if the argument is non-negative, then the output of the ReLU is the argument itself. If the argument is negative, then the output of the ReLU is 0. And we need to test to see if this design works for Alice. So in this example that we had before, yesterday Alice was exercising, and today Alice woke up feeling normal. So we have the W, H of n minus 1, which is this red part right here. To that we add the driving force or the input feature pre-multiplied by U, and that's the blue part here. And we have the bias vector, which we define to be this. Let's go ahead and add these guys up. Again, multiplying by this vector allows us to pluck column 1, which is right here. Multiplying by this vector allows us to pluck column 1 from this guy, which is here. And this is just the b vector, which is not multiplied by anything, so we go ahead and add that there. And we add the three terms together, we get this third of the vector, this third of the vector, and this third of the vector. If you'll notice, this guy following the routine is the only one with positive numbers. The other guys are either zeros or negative numbers. So far it seems to be behaving well. Now we know that the current state is going to be V pre-multiplying the activation function applied to this vector. And the Rayleigh activation function says, hey, if you're non-negative, copy over. So 0 to 0, 1 to 1, 0 to 0. But if you're negative, replace it with a 0. So this guy gets replaced with a 0. This one's fine. This gets replaced with a 0. This one's fine. This gets replaced with a 0, and this gets replaced with a 0. So now we have that the current state for today is V pre-multiplying this output of the activation function. But the state has to be a 3 by 1, not a 9 by 1. And we know that all the vectors are 0 except the correct one, which is sleep. So if we look at it, this vector associated with the routine, which means that today she should sleep, is correct. And all the other ones, because of the activation function, are actually 0. And because our activation function is designed to make sure that these wrong selections are always 0, then we know we can add the three segments by choice of our matrix V. So we're going to choose V to be this matrix right here. Now there's a lot of colors in here, but there's a method to the madness. Just keep in mind that I want to add this element with this element with this element. The first element of the three segments, right? The routine segment, the I woke up tired segment, and I woke up rested segment. I want to add these three. I know that only one of them is going to be non-zero. So this matrix is designed so that the first row of V adds elements 1, 4, and 7, the three green elements here. The next row, row number 2, adds elements 2, 5, and 8. You can see element 2, element 5, and element number 8 are going to be added by this second row right here. And the last row of V adds elements number 3, element number 6, and element number 9. And you can see here in positions 3, 6, and 9, there's a 1, which means when I multiply this by that, when I do that inner product, it's going to add these three purple values. If the activation did its job properly, then only one of these guys is going to be 0 at any given time. So when I do the matrix multiplication of these two guys, I'm going to get the three greens added on row 1, the three oranges added on row 2, the three purples added on row number 3. And that's going to give me 0, 1, 0, which is the vector associated to the verb sleeps. Alice sleeps. Today, Alice sleeps, which is exactly what we wanted it to be according to our routine. So this indeed is the correct answer. Let's test it again. So in this case, let's assume that yesterday Alice was sleeping all day long. So she was sleeping yesterday, that's the vector for sleeping at time n-1. And today she woke up feeling normal. That means that she's going to follow the same routine that she normally does, and the day after sleeping in, she spends the day sitting down. So we're hoping that our system will output the verb sits for h of n. Let's check if this is the case. We know that for Alice sleeping yesterday, we take the W matrix and we post-multiply it by the vector for sleeping. And then we add u times the driving function, which in this case it's normal. Today's a normal day. She follows her routine. And finally, there is the bias term right there. Now, when you add the three of them, what do you get? Well, this w is post-multiplied by a vector of all zeros except for a 1 in the second position. That means we pluck the second column of w and we copy it here. That's the second column. Then the next blue segment says that here's the U matrix and we post-multiply it by a vector of all zeros except for a 1 in the first position, which means we grab the first column and we copy it here. And here's the bias. Let's go ahead and add those guys together, and this is the argument to the activation function. Now we know that the current state for today is going to be V pre-multiplying the activation function of this vector. And we know, again, this 0 stays the same, this 0 stays the same, this 1 stays the same, minus 1 gets turned into 0 because of the ReLU function. This 0 is the same, minus 1 goes to 0, 0 stays the same, minus 1 goes to 0, minus 1 goes to 0. So now we know that we post-multiply V by this output of the activation function. We go ahead and apply the same V that we used before, and we're going to get that the three green elements are zeros, the three orange elements are zeros, and the purple elements are 1, 0, 0. And upon adding these guys together, we get the vector for sits, which is exactly what we were hoping to get. So far, our selection of matrices has worked out great. But for those of little faith, let's go ahead and do a couple more examples and then we'll call it quits. Let's say that yesterday Alice was sitting. This is the vector for sitting. This was yesterday at time stamp n-1. And today she woke up feeling tired. That means that the routine should be ignored and she should sleep today. Let's see if this works out. Well, here's the w. This vector here with the 1 in a third position says we should grab the third column of w. This is Alice woke up feeling tired. With the 1 in the second position, that means we grab the second column of u. So when we multiply these out, we get, because this is a 1 here, we just pluck the last column of w and we copy it here. Because there's a 1 in the second position and all the others are 0, we grab the second column of u and we copy it here. And then there's b, that's just b. Go ahead and plug in and add those element by element. And we know that the current state for today, we want it to be that she's tired so she sleeps today. We want this to have an emphasis on sleeping. The activation function is the one that allows us to map zeros to zeros, minus 1 to 0, minus 1 to 0, 0 to 0, 1 to 1, that guy stays, 0 to 0, 0 to 0, minus 1 to 0, minus 1 to 0. And then the current state, we go ahead and pre-multiply V matrix, and we add all the three greens together, all the three oranges together, and all the three purples together, and we get the vector corresponding to sleeps. Today, Alice feels tired. So no matter what she did yesterday, today she's going to sleep. That is correct. One last example to make sure we're all on the right track. Let's say that yesterday Alice exercised and today Alice feels rested. We know that if she feels rested, no matter what happened yesterday, today she's supposed to exercise if she feels rested and energetic. Let's see if this works out. We know that when we post-multiply this matrix with a vector all zeros except a single one in the first position, means we're going to grab the first column. And when we post-multiply u by this vector that's all zeros except a single one in the third position, we're going to grab the third column. So that means that when we multiply these guys out, we're going to get the first column copied here, the third column copied here, and here's the bias vector. We go ahead and add those guys together, and as you'll see, all these are zeros and minus ones. The only one that has a positive one is the one associated to exercise, the one that is always exercise. Again, the current state is equal to V pre-multiplying the output of the activation function, and we map all the minus ones to zeros, all the zeros to zeros, and all the ones to ones. And therefore, the current state, we're going to use the V matrix to go ahead and add the greens together, the oranges together, and the purples together. And here you're going to get all the greens added together, oranges together, all the purples together is going to give us exactly the vector for exercises. So no matter what she did yesterday, we don't care what Alice was doing yesterday. Today she woke up rested. So today she's going to exercise. So that worked out well. Now, what we're going to see in our next class is training and backpropagation through time, BPTT. And we're also going to discuss the problems that crop up and how LSTM and also GRUs can help us prevent or mitigate these problems. These were invented to solve the vanishing gradient problem in RNNs, and these are associated to long-term dependencies. So they were invented to solve the vanishing gradient problems and the exploding gradient problems that can also be understood in terms of stability of a system's dynamics, again, from the engineering perspective. What happens is that during training, first of all, you start by defining some loss function. Then you compute the gradients of the loss function with respect to the weights, right? The W, the U, the V, and the bias vector. And this involves backpropagation through time. So you end up with a chain of derivatives, basically a long product of these derivatives. And these will just be the product of the Jacobian matrices, which are just matrices of partial derivatives. Now, if the eigenvalues of the Jacobian are all inside the unit circle, then the system is stable and the gradients vanish exponentially. What does this mean? It's that the RNN forgets the long-term dependencies because initial state perturbations die out. Now, you may or may not want this because long-term dependencies may be needed for your design. The other problem is the exploding gradient problem, and that occurs when gradients, again, you have a long string of Jacobians multiplying, and the gradients grow exponentially as they backpropagate. Now, dynamically, this corresponds to an unstable system, and if the eigenvalues of the Jacobian are outside the unit circle, the system is unstable and the gradients will explode exponentially. Now, training becomes unstable because of this uncontrolled gradient growth. So LSTM and GRU introduce gating mechanisms to regulate the memory, but that's going to be what we talk about next time. Thank you for joining us, and I hope to see you on our next lecture.